Take a spinning top. You know the kind a child plays with. You spin it, and you can see it rotating. The surface is moving, points on the edge going around and around. Now, electrons have something called spin, but here's the problem. They're not spinning. Not in any way you can picture. They're not rotating. There's nothing moving around. You see, when physicists first discovered this property back in the 1920s, they called it spin because mathematically it looked like angular momentum. And angular momentum is what a spinning object has. So they thought, aha, the electron must be spinning like a little ball. That seemed reasonable. Makes sense, right? You've got this tiny particle. Maybe it's rotating on an axis, like the Earth rotates. Very natural picture. Very comfortable. But then, well, we measured some things, and it can't work that way. It just can't. When we say an electron has spin, what do we mean by that? What are we actually talking about? Well, we mean it has angular momentum. That's a definite thing. Angular momentum has a value. You can measure it. It's conserved in interactions. All the mathematics that applies to a spinning top, all those rules about angular momentum, they apply to the electron too. So you might say, fine, it has angular momentum, so something must be spinning. But what? An electron, as far as we can tell from every experiment we've ever done, is a point. I mean, it has no size, zero radius. Not very small. Actually, zero, as far as we can measure with the best equipment we have. Now, think about that for a moment. What's there to spin? You need a surface, points at different distances from an axis. But there is no surface, no edge, no here versus there on an electron. Let me give you an example of how careful you have to be with words in physics. This bothered me when I was younger. Suppose you're a doctor, and someone says, Mrs. Smith has lumbago. Now, what did you learn? Well, you learned that Mrs. Smith has pain in her lower back. That's what lumbago means, lower back pain. But it sounds like a diagnosis, doesn't it? It sounds like you explained something. Oh, she has lumbago. That's why her back hurts. No. You just gave the pain a fancy name. You didn't explain why she has the pain. You didn't tell me about herniated discs or muscle problems or anything that would actually help understand what's going on. Now, I'm not saying spin is exactly like lumbago. We know more about spin than just giving it a name, but I'm showing you that you have to be careful. The word doesn't explain the thing. You see, in physics we have this property. We measured it. We can predict with it. We can calculate with it. And we called it spin for historical reasons. But you have to decide what level of explanation satisfies you. I could tell you, electrons have spin, it's a quantum property, and that's that. Some people are satisfied. Others want to know, yes, but why do they have it? What is it really? And that's a harder question, much harder, all right? Here's what we know for certain. If you take an electron and pass it through a magnetic field in an experiment called the Stern-Gerlach experiment, it splits into two beams, not a spread, not a blur, two beams. Otto Stern and Walther Gerlach did this back in 1922. They were actually looking at silver atoms, not individual electrons, but the principle is the same. They heated silver in an oven, shot the atoms through an inhomogeneous magnetic field, and watched where they landed on a detector plate. Now, if these atoms were classical magnets that could point any direction, you'd expect a continuous smear on the detector. Every possible angle, every possible orientation. But that's not what happened. They got two spots, just two, up and down. That means the electron can only have angular momentum in two directions. Up or down, if you like. We measure it, and it's always 1/2 of Planck's constant times h bar. Always that value. Never zero, never anything else. A spinning ball can spin at any speed. You can spin it faster, slower, stop it completely. The angular momentum can have any value from 0 up to whatever you want, not the electron. The electron's angular momentum is stuck at this one value, and the direction can only be one of two ways. Quantized, we say. It comes in chunks. Now you might say, but why can it only point two ways? Why not 3 ways, or 100, or any direction, like a real spinning object? Well, that's quantum mechanics. That's one of the strange rules. Things come in discrete amounts, not continuous. The universe is built that way, and we don't know a deeper reason. At least, not in terms you'd find satisfying. But here's something that really shows it can't be physical rotation. Let's pretend, just for fun, that the electron is a little spinning ball. We know how big the angular momentum is. We know that if it had a size, it would have to be smaller than about 10 to the minus 18th meters. That's our best limit from experiments. Incredibly tiny. All right, you've got angular momentum, you've got a maximum size. Now you can calculate how fast would the surface of this little ball have to be moving. You do the arithmetic and you find out the surface would have to be moving faster than the speed of light. Much faster. Maybe 100 times faster, depending on exactly what size you assume. But nothing can move faster than light. That's a fundamental rule. The theory that predicts the electron's spin in the first place, quantum mechanics combined with relativity, that same theory forbids anything moving faster than light. So the electron can't be a spinning ball. The mathematics eats itself. It's inconsistent. The picture destroys itself. Think about what that means. You have this property that acts like rotation, that has all the mathematics of rotation that we even call rotation. But it's not rotation, not in any physical sense. It's something else, something that doesn't have a picture you can draw with your pencil and paper showing how it works. Now, for a physics student, I could tell you more. I could tell you that spin is described by something called Spinors. The mathematics says that when you rotate an electron by 360 degrees, all the way around, you don't get back to where you started. You have to rotate it 720 degrees, twice around. That's bizarre, right? You turn something all the way around, and it's upside down. You have to turn it again to get back. Nothing in your experience does that. But mathematically, that's how spin 1/2 particles behave. There's actually a way to demonstrate this with a belt or a ribbon. It's called the Dirac belt trick. You take a belt, attach one end to something fixed, hold the other end, and give it a full twist. Now it's tangled. But if you move your hand around in a certain way, keeping the twist, and complete a second full rotation, the tangle disappears. The belt is flat again. It's a topological thing. It shows that there's something mathematically consistent about needing 2 rotations to get back to where you started. But don't worry about the equations. The point is it's mathematically different from ordinary rotation. It has strange properties that nothing in your everyday experience has. And here's another thing. The electron's magnetic moment, the strength of the magnet it acts like, is almost exactly twice what you'd calculate if it were a spinning charged ball. Almost exactly 2 times. We call that the G factor, and for the electron it's very close to 2. Why 2? Well, Dirac's equation, which combines quantum mechanics with special relativity, predicts exactly 2. Then, when you include quantum field theory effects, tiny corrections from virtual particles popping in and out of existence, you get 2.002319, and so on. We've measured it to incredible precision. Matches the theory to 11 decimal places. That's one of the most precisely verified predictions in all of physics. But it doesn't come from the electron spinning. It comes from this intrinsic quantum property. You know, people sometimes try to help. They say, oh, I'll give you an analogy. It's like the electron is a little magnet. A bar magnet has a north and south pole, and it can point up or down. All right, let's try that. An electron does create a magnetic field. It acts like a tiny magnet. So you could say spin is like the electron being a little bar magnet that can only point 2 ways. But I'd be cheating you if I left it there. Because now you'll ask, well, why is the electron a magnet? And I'd have to say because it has spin, you see? I'd end up explaining the magnet with the very thing I was trying to explain with the magnet. We're going in circles. Or someone might say, think of it like the electron has an arrow attached to it. The arrow can point up or down. There, now you have a picture. But that doesn't help either. Because you'll ask, what's the arrow made of? Is it part of the electron? Does it have mass? Can it break off? No. There's no arrow. I just made that up to give you a mental picture. But the picture's wrong. It's not a real arrow. The truth is, I can't explain spin in terms of something more familiar to you. I can't say it's like this thing you already know without lying. because it's not like anything you know. This is one of those fundamental things we start with in quantum mechanics. It's a basic property, like electric charge. An electron has charge, it has mass, and it has spin. These are just properties, intrinsic properties. They're not made of something else. I don't understand it in terms of something else either. Nobody does. We just know it does this. We can predict with it, calculate with it, build computers with it. But asking, what is it really? That's asking for a picture that doesn't exist. And maybe that's the deepest lesson here. Maybe the universe at its most fundamental level doesn't match our intuitions. Our intuitions evolved to deal with tigers and falling rocks and where to find food, not with quantum particles. Now this means something remarkable. The Pauli Exclusion Principle, the rule that says no two electrons can be in the same quantum state, that depends on spin. Wolfgang Pauli figured this out in 1925. He said you can't put two electrons in exactly the same state if they're fermions, particles with half-integer spin. If electrons didn't have spin, that rule wouldn't work the same way. And if that rule didn't work, atoms wouldn't have their structure. Chemistry wouldn't exist the way it does. Think about it. In a hydrogen atom, the electron sits in the lowest energy level. Fine. Now, helium has two electrons. Where do they go? Well, they both go in the lowest energy level, but one has spin up and one has spin down. That's two different states, so it's allowed. But you can't put a third electron there. The exclusion principle says no. So lithium, with 3 electrons, has to put that third electron in a higher energy level. And that changes everything about how lithium behaves chemically. That's why lithium is reactive. That outer electron is easy to remove. The entire periodic table, the whole structure of chemistry, depends on this. Different elements have different numbers of electrons, and they fill up the energy levels following this exclusion rule, and that's why elements in the same column have similar properties. Carbon, silicon, germanium, they're all in the same column because they have the same number of electrons in their outer shell. And that's because of how spin and the exclusion principle work together. You wouldn't have molecules. You wouldn't have DNA. You wouldn't have life. Your entire existence depends on this weird property that we can't explain in familiar terms. The fact that electrons have this strange intrinsic angular momentum that isn't rotation. That's why you're sitting here watching this. Without spin, all the electrons would collapse into the lowest energy state. There'd be no chemistry, no complex structures, no you, no me. The universe would be completely different. Just hydrogen and helium, probably. No stars like the sun, because the nuclear reactions that power stars depend on quantum mechanics, and quantum mechanics depends on spin. Everything would collapse. Matter as we know it wouldn't exist. Now, if you were taking a quantum field theory course, advanced stuff, I could tell you that spin comes from the symmetries of space-time. The mathematics of relativity and quantum mechanics together predict that particles must have spin. It's not optional. When you write down the equations that describe how particles behave in a way that's consistent with both quantum mechanics and special relativity, spin falls out automatically. You don't put it in by hand. It emerges from the mathematics. Eugene Wigner worked this out. He looked at the symmetry groups of space-time, the Poincare group, and found that particles are classified by their mass and spin. Those are the two fundamental labels. In fact, the theory predicts you can only have certain values of spin. You can have spin 0, like the Higgs boson. Spin 1/2, like electrons and quarks. Spin 1, like photons. Spin 2, like the graviton, if it exists. And so on. Electrons happen to be spin 1/2 particles. Quarks, too. We call them fermions. Photons are spin 1. We call those bosons. And the statistics are different. Fermions obey the exclusion principle. Bosons don't. You can pile as many photons as you want into the same state. That's how lasers work. All those photons marching in lockstep. Same frequency, same phase. But even that doesn't answer what is it really. It tells you it must exist. It tells you what values it can have. But it doesn't give you a picture of little gears turning or balls spinning. And you know what? Nobody knows if there is such a picture. Maybe the universe doesn't work that way. Maybe at the bottom, reality just has these properties, and our job is to describe them mathematically. not to draw pictures of them. Maybe asking for a picture is asking the wrong question. The name spin is historical. It stuck because the first scientists who found it thought it might be rotation. Samuel Goudsmit and George Uhlenbeck proposed the idea in 1925. They were young students, and they suggested that electrons might be spinning to explain some spectroscopic data. Their professor, Paul Ehrenfest, pointed out the problem with the speed of light I mentioned earlier. But by then, the name had stuck. And honestly, we don't have a better word for it. By the time we knew better, everyone was already using the word. Thousands of papers, textbooks, all using spin, so we're stuck with it. Just like we're stuck calling it a particle, even though it's also a wave. And stuck calling light a wave, even though it's also a particle. Physics is full of these terrible names that confuse everybody. Confuse students, confuse the public. Sometimes even confuse the physicists. I remember when I was learning this stuff, I kept trying to picture it. I'd imagine little electrons spinning like tops. And then I'd calculate something and get the wrong answer. And my professor would say, well, you can't think of it that way, so I'd try another picture. Maybe they're vibrating? No. Maybe they're wobbling? No. Nothing worked. Finally, I gave up on pictures and just learned the mathematics. And you know what? The mathematics works beautifully. It predicts everything correctly. The pictures were holding me back. But the mathematics doesn't lie. The experiments don't lie. The electron has this property. It's real. It has consequences. It makes the universe work the way it does. We use it every day. MRI machines, magnetic resonance imaging, they work because of spin. The nuclei in your body have spin, and we can flip them with radio waves, and they emit signals we detect to make pictures of your insides. Quantum computers, or the ones people are trying to build, many of them use spin. You can have a spin up representing 1, spin down representing 0. And because it's quantum, you can have superpositions both at once, and that's where the power comes from. Hard drives in computers use spin. The magnetic domains that store your data, those depend on the spins of electrons aligning. All those videos and photos on your computer, they're stored as patterns of electron spins. Even the electricity flowing through wires to power your lights, that depends on electrons, and electrons have spin. The whole world of electronics, computers, telecommunications, it all rests on quantum mechanics, and spin is central to quantum mechanics. So it's not just abstract philosophy, this weird property that we can't picture. It's running the modern world. Strange business, isn't it? That the universe has these fundamental properties that we can measure, predict, use, but can't picture, can't draw, can't explain in terms of spinning balls or anything else familiar. We can build trillion-dollar industries on it. We can use it to save lives in hospitals. We can store all of human knowledge on devices that fit in your pocket. But we can't say what it really is in a way that would satisfy your intuition. That's roughly where we are. The universe doesn't care whether we can picture it or not. It just does what it does. And our job is to figure out the rules, even if the rules don't match our everyday experience. Even if the rules seem bizarre and counterintuitive and impossible, because they work. That's the test. Does it predict what we observe? Yes. Then it's right, whether we like it or not. Interesting.